At Gateway, Dr. Soifer is our staff developer, and the concepts she will discuss tonight are among the foundations for the math program that is in place in our school. And our moderator will be Heather Ironside. Heather is the Director of Language and Literacy at Gateway. And so I'm going to turn this over to Dr. Lydia Soifer. Welcome.
Thank you. Good evening, Mrs. Salzman, and good evening, everyone who has joined us to learn a little bit more about math. Before I start, I want to make sure to thank my colleagues at several levels. Certainly Valerie Rafel, Vicki Messler, and Heather Ironside, who have been so instrumental in helping me develop these presentations, and to all of my colleagues at the Gateway School who work so very hard to continue to grow and learn and provide this kind of superb instruction in math and in all of our subjects at Gateway School. Ms. Ironside will be taking your questions, which I will do my best to answer at the end. And so let's start this journey on the road to Mathland.
Dr. Soifer, I'm just going to interrupt for 1 second. For those of you attending, there is the option to do a Q&A at the bottom of your screen. You can put any questions that you have for Dr. Soifer in there. And then in the chat, if you have any additional questions or technical kind of questions, feel free to put them in there, and we have people monitoring both.
Okay, thank you, Heather.
Welcome.
All righty, so our very first slide. I'm so proud when I can make anything work on the computer, and certainly long distance. So why indeed is math so important? It is important because math is the language of logic. That is a direct quote from Dr. Jackie Chen of the Erickson Institute, which is a resource for you to consider when you are investigating topics related to math. The Erickson Institute is replete with information for parents and teachers on early math development. What we know is that math builds reasoning, which leads to comprehension. That is our goal for the children, for them to have good comprehension. It helps in the development of a mentally organized way of thinking, which is crucial. And to make that happen, that kind of mentally organized way of thinking, math education is necessary at a very early age. Math has a great predictive power and ability. Early math skills, there is research that tells us, as much as we've been focused on literacy, that early math skills have some of the strongest predictive power of academic success in company with literacy and attention. That work comes right out of the journals of developmental psychology. So we are well aware, and have been for a while, that math development is crucial in our youngest children. Now, I will tell you that counting doesn't count. It's sort of like reciting the alphabet. We need to be able to have the children understand what the numbers mean, not just their names. And in a little while, we'll be talking about the concept of mathematizing our little ones so that they develop earlier math skills. It's also important to know about the economics of math. There has been extensive research that shows that for both men and women, a history of poor math skills is associated with lower rates of full-time employment and higher rates of employment in lower paying, more manual occupations. So math is important. Some of you have seen this image before. Who is this child? I developed it with colleagues many, many years ago, as you can see from the date, 2006. What we train teachers to do is when any teacher looks at a child, and similarly at some level, when parents look at a child, they have to say to themselves, who is this child? What is his or her inherent neurology? What kind of personality and temperament has he come to the world with as I see him now? And then there are these interlocking circles: cognition, attention and executive functions, working memory, emotional functioning, language, academics. How is he being taught? Is she being taught in the way she needs to learn? And the impact of sensory motor aspects of functioning. All of these happen to a youngster, are happening to a youngster all of the time. So when we are thinking about math instruction, we are always holding on to the concept of who is this child and what enables or disables him in this makeup to enable her to readily learn math and to use math going forward. So try and keep that image in your mind. So as we take a look at this slide, let's take a look for a little bit of time to address the way we at Gateway School, and we hope and assume that in the larger educational world, want to see math skills being built in our youngest children. So I'm going to spend a little bit of time talking about the nature of math skills in little kids, what we have to do to lay foundations for them in order to build skills upon those foundations, as well as what those skills are. We're going to stress the importance of play, and that play has to include the language and basic activities of math. That cannot be stressed enough. And we'll talk again more about mathematizing and how do you make this available, these mathematical skills in the context of play and the context of everyday life, available to our little ones. I beg your pardon. So what we're looking at now is the early development of math skills. And I'm going to stress for those of you who are parents or those working with the youngest children, as you can see, infancy, toddlerhood, and preschool, is to stress math talk as it indicates. We know from the research that humans are born with an innate number sense. Researchers have discovered that babies who are years and years away from being able to say 1, 2, and as they are inclined to say, 3, actually already have some sense of what counting means. Babies who hear counting realize internally that it's about quantity. I beg your pardon. There is a distressed Shih Tzu barking at me. Allow me a moment of redirection. Excuse me. She can't count. She actually can't see or hear, but she can bark. And so forgive me for the interruption. Alrighty. So what we know is that out of some research that was done at Johns Hopkins, and this is really, really intriguing to me, is that the cognitive science researchers at Hopkins noted that although little ones are years away from understanding the exact meaning of number words, babies are already in the business of recognizing that counting is about number. And indeed, babies are more sophisticated about the world than we previously believed. We know more and more about them now. They're already trying to make sense of what the adults around them are saying, and that includes the domain of counting and numbers. They did a wonderful, totally cool experiment with 14-month-old infants. The babies, these little 14-month-olds, watched as toys or little dog dolls or cars were hidden in a box. And the babies couldn't see what was in the box, but they could reach into it. Sometimes what the researchers did in one condition, they counted each toy aloud as they dropped it into the box, saying, look, 1 doggy, 2 doggies, 3 doggies, 4 doggies. So they were counting and identifying. Other times, the researchers simply dropped each toy into the box saying, and this, and this, and this, and these doggies, without counting. Without counting, the babies had a hard time remembering that the box held 4 things. How do we know that? Because they tended to become distracted after the researchers pulled out just one, as if there was nothing else in there to see. But when the toys were counted when they were put in the box, the babies clearly had anticipation, and they expected more than one to be pulled out of the box. They didn't remember the exact number, but they knew that there was an approximate number. There was more in that box. Moreover, we know that the roles that parents play in laying foundations should not be underestimated. Children's early experiences with math in the home set the stage for later achievement in school. And that points to the importance of providing rich opportunities for young children to engage in math from an early age. That's not to say that parents should be teaching to count the way some parents and even some schools have begun stressing what they call reading by having kids recite and learn letters in very early preschool. If you're still in Pampers, you shouldn't be reciting the alphabet. Rather, this takes the following very simple and delightful form of what is referred to in the literature as mathematizing a little one. That is, to use math language in the routines of everyday life, either as a game or an entertaining way to solve problems. For example, look at all the ladybugs on this page, honey. Let's count them. I love ladybugs. Let's count them. Or finish up. You have 3 more Cheerios to finish in your bowl. Wow, you really stacked those blocks so high. That's a tall tower. Honey, can you bring mommy 2 socks, please? Or when going up and down the steps, let's count up. 1, 2, 3, and then down. 1, 2, 3. This kind of parental math talk that can also be included in nursery and toddler classrooms involves both counting and number talk and spatial talk, higher, taller, and spatial thinking, shape terms like circle or triangle or rectangle or cone in an ice cream cone, dimensional adjectives, big, little, short, tall. All of this is building the language of math, which we will talk about in a little while, as well as spatial feature terms. Curvy. Oh, that's the edge, a line, a corner, that's straight. Today, I watched a lesson where they were making reference to the word fragment, and it was in an English lesson, an English language lesson. And one of the little boys held up a piece of apple, a slice of apple, and the one piece had been broken off, and he said, look, it's a fragment. It's a piece of the whole slice. That's the language of mathematics as well. Parental math talk, we know, varies upon socioeconomic status. And the higher level of SES, parents talked more in math language. And the research shows that people of lower socioeconomic background or those who have had negative mathematic experiences were less likely to appreciate the importance of math talk and therefore less likely to use it. Such a history of what is often referred to as math anxiety is a completely different subject, but not unrelated. So we know that math talk is important in the household. In addition, and what we know is that there are expectations for reading that have been particularly stressed over time, and people have been told that reading is more important than math, and that math is less interesting and exciting and desirable. But we know, with the emphasis on STEM teaching, that that is no longer true. So mathematizing our children is something we want to consider when we are dealing with the littlest among us. Now, play is actually learning for children. It's not the same as it is for us. And certainly it provides a great opportunity for building math skills. We are well aware that pretend play is a precursor to reading comprehension. We've known that for a while. We know that as part of the nature of story development. Children play out stories, what are called narratives, and developmentally over time they acquire what are called story grammars. There is a parallel in the concept of math skill development. Whose tower is higher? Let me see. How many more blocks do I need? Oh, what can I do to make this balance? So that kind of questioning, that kind of language use facilitates the language of math and math thinking. I would tell you as well that the emphasis on play by the Gesell Institute is quite extensive. When you think about a set of skills, classifying, red bugs and blue bugs, how many do we have? Are there more? Exploring magnitude. Wait, is this big enough? Am I going to be able to get that under? All sorts of sequencing skills, the use of the rainbow mnemonic, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet, to create sequences of flowers or sequences of houses, or in the case of one little girl who drew sequences of her favorite animal, cats. In addition, by saying number words referred to as enumerating, or recognizing the number of objects, or reading and writing a number in the midst of play. Right? So by graphing, we see that now. I see it more and more in early childhood classrooms. How many children have sneakers with Velcro, and how many children have sneakers with laces? And we make graphs. How many children are wearing blue shirts today? So that you can create visual representations of numerical relationships. And then there's also, in play, investigating the dynamics between different parts of a whole. When I have talked at other schools, sometimes I will get information fed back to me about what worked and how it was done in a classroom. And one of the teachers sent an image of a Play-Doh pizza pie that they made, and they cut it into different size slices to talk about the different sizes that slices of pizza could be. So in the midst of a play activity, there was mathematizing. The very best way for parents to mathematize their children is to use math in the daily routines of life, either as a game or in an entertaining way to solve problems. And as you can see on the slide, 1 little, 2 little, 3 little Indians, or little piggies, or little tickles, whatever it is, by using this kind of language, it becomes a part of the children's repertoire that is beyond the development of the vocabulary of their world in terms of what they see and touch. Before school, children need to know a great deal. And as you take a look at this, these are the developmental states of math learning. And I'll mention each of them very briefly. This is the work of Felissier, and I love the title of the article. It's a 2018 piece that says, "Why early math is just as important as reading." So let me tell you briefly what these developmental states of math learning are. Number sense is understanding quantity, grasping concepts like more and less, larger and smaller. And this one, think for a minute after I say this one, recognizing the relationships between single items and groups of items. For example, 7 means the same thing as one group of 7 items. 7 means the same thing as one group of 7 items. There are 7. Understanding that symbols represents represent quantities. The number 7 is the same as the word seven, S-E-V-E-N. Being able to make number comparisons. 12 is greater than 10. 4 is half of 8. You're already starting to hear the language of math, which will come up again in a little while. And understanding the order of numbers. First, second, third. We do this, we talk this way. We need for them to understand this way as precursors of mathematics learning. When we look at representation, realize in the same way that children learn to read, that the letters of the alphabet represent to some extent the sounds that we make, using symbols and words to represent numbers, so that the number 7 has a quantitative nature to it. Spatial shapes, shapes and spatial relationships have to do with geometry. For those of us who don't see in 3 dimensions, managing that was always a great deal of fun. Then there's measurement, comparing and communicating about size, using a ruler, who is taller, who is bigger, which one is wider. You do that all the time. You can do that in the mathematizing process by saying, let's take a look at this box and measure how tall it is, and then measure the shelf and see if it will fit in. Similarly, patterns, recognizing and making patterns, repeating patterns of 3 greens, a blue, 3 greens, a blue, help deal with the issues involved in and sequencing. And then ultimately, in terms of problem solving, that becomes the foundation of word problems. Early math is just as important as early reading. Until fairly recently, math had been nearly absent in American preschools and pre-K classes. One study that I pursued calculated that in preschools, where kids spend up to 6 hours a day, math gets taught less than a minute during the day. And I will tell you, based on personal experience, that when I questioned the 2nd grade teacher of one of my sons about why they never did any math work and why he never had any homework, she had the temerity to look me right in the eye and say, oh, I hate math. They'll learn everything they need to know next year. And we'll get to that as a very, very, very serious error in judgment in relation to the way math skills are acquired. It's also important to note that when you have someone who hasn't been well trained or doesn't love the teaching of math, those minutes of math instruction may not be particularly well done. Reciting numbers is not any more potent for learning math than reciting the alphabet is for learning to read. It teaches number order, but it does not teach them any number sense any more than singing that giant letter LMNOP in the alphabet song teaches phonological or phonemic awareness. So let's talk a little bit about what the different kinds of skills are necessary or expected in kindergarten, 1st and 2nd grade, which is our focus as we talk about the early development and the first stages on the road to Mathland. Take a look at all of these skills that are expected of our kindergartners. So much of what we do at Gateway as we prepare the children by laying mathematical foundations for them is multisensory, hands-on, with clear, explicit instruction that is repeated and rehearsed. We use that direct, explicit, multisensory instruction, and we'll talk a little bit more about that later as a simple matter of course. As I share the next few slides with you, I imagine that you are reading all of this. I want you to be awed, not necessarily by me, although I might appreciate that, though I won't know it, but by the amount of knowledge that our little ones are expected to acquire and use in the first 3 years of school, kindergarten, 1st and 2nd grade, which stresses why we have to put more energy into early mathematics instruction as we deal with our little ones. That's kindergarten. Here comes first grade. Now they have to be able, and you don't need me to read this to you. You can read it to yourselves while I'm talking to you. Math standards and curricula can vary by location or by school. So these are not absolutes for your school or your school district. What you've got to be able to do is, if you have any questions, is to speak with school administrators and teachers to determine what math skills are expected by grade in your school. But can you begin to see the pattern as cumulative? All right, there's a dynamic here with language and with memory and with cognitive functions such as sequencing, comparing, and directionality, which is why that image of who is this child has to be a part of the way you are thinking about the children. Now take a look at the second grade skills. All right. Counting up to 1,000, relationships between larger numbers, subtracting within 1,000. You're 7 or 8 years old now. The expectations have grown. Now we can add the demand of activating prior knowledge. What did I already learn about this that I can use for this new learning? As well as, and please take a look at some of the numbers, not the words representing numbers, but the actual digits, all right? And the visual, because you have to consider the visual spatial relationships and symbols like the comma in 1,000, all right? Or a period in 100.16. Suddenly the periods and the commas have a different meaning than they do in the literacy context. So the children have to shift in and out and use their prior knowledge and activate it or think in math language. All right. Take a look at this. These are the number of skills, math skills for grades kindergarten through 2. That's a lot to learn, to retain over a short period of time. This is the work of the researcher Uzi, who said that math, like learning a foreign language, is a great challenge. Math is so hard because it builds so relentlessly year after year. And it's important to keep that word in mind, cumulative. Any skill not mastered in 1 year will make work the next year harder. Math learning is essentially unrelentingly cumulative, which makes it easier for children to have accumulated deficits when they are not being well taught or appropriately taught for their needs, or they have particular math deficits. My dearest friend in the world was a New York City mathematics teacher for more than 35 years. She was a teacher of remarkable skill and was acknowledged by the City of New York as Teacher of the Year. And what is concerning her is, in this period of time when the children are being educated in an alternative way, is that math learning is cumulative. And she is expressing great concerns, we can add to our list of concerns, that it will be harder and harder for the kids who are not acquiring all the skills to build to the next level. Let's think about it in a slightly different way in terms of the cumulative nature. Think about a language like Latin. For those of you who learned Latin either in college or in parochial school. Math, for a specific example. Algebra, like Latin, is a language already. So you have to learn the language of math the same way you learn any other foreign language. And you have to learn a lot of it, and in a very, very short period of time. There are 5 major math concepts for first and second grade students. And I want to make an important point here about algebra. Most of you will remember algebra as part of middle school, but you can see that we start with addition and subtraction, the notion of number sense or understanding quantity, measurement and data collection, geometry, and then algebraic thinking. Algebraic thinking in the first and second grade. In reality, algebraic thinking is introduced far, far before puberty. As you'll hear in a little bit, here at Gateway, we have adapted Singapore math for our students. So even early on in Singapore math, there's an algebraic component. When presenting the following to a youngster, 1 plus what would give you, and you might have heard me use my voice to emphasize what, that representation of what is actually a symbolic representation of another concept. In this case, what we typically call X, all right? 1 plus what, 1 plus X equals, all right? So basic algebra is in the field of mathematics, that's one step more abstract than the concepts of arithmetic. Remember, arithmetic is the manipulation of numbers through basic math functions. Algebra introduces a variable. It sort of stands for an unknown number or can be substituted for an entire group of numbers. So algebra in first and second grade is a branch of mathematics that deals with symbols and rules for manipulating those symbols. So in elementary algebra, those symbols, today written as Greek letters, represent quantities without necessarily fixed values that we call variables in the first and second grade. Math constructs that early on. This next slide is an important one for all of you to focus upon. I can't begin to emphasize enough the importance of strategy-based instruction. All right? This is true for all learners. All right? It engages children actively in understanding the why, the how, and the what of what it is they are doing. Strategic instruction, not just telling them what to do it this way, and having them imitate. Strategic instruction develops a higher level of thinking, a problem solving, an analytical approach that will serve them in all aspects of academics, all right? So this slide is also an essential one, as you'll see, when we begin to discuss diagnostic teaching. But take a look, again, the importance of these cognitive characteristics, these attentional characteristics, these thinking characteristics. What you're seeing here are aspects of executive functions and cognition, and they are side by each, what strategic learners can do and what at-risk learners do. Again, very, very important when you have to be in the position, as you always should be, of diagnostically teaching, figuring out what this kiddo knows and needs from you as a teacher. So what's a teacher to do? This is an overview slide, everybody. This is what I'm going to be talking next is what you could do, because this is what we do at Gateway School for our youngest all the way up to the middle school. It has become the pattern of our teaching that makes us so successful with these boys and girls. I can't discuss them all in depth because I've only got an hour or so, but rather for you to begin to explore further and conceptualize your students' needs. So I'm going to talk about each of these one at a time. As Mrs. Salzman said in her introduction, my fascination has always been with language, but language is a key element of math. All right? So while numbers are at the heart of computation, language is used to discuss the computation. Language is used to discuss the theory and various approaches in math. Language is necessary to discuss the context and so on. So there's some very interesting research to share with you as you look at this. Math is its own language. There are enormous challenges in the language of math. Listen to this research. You'll find it particularly interesting in the language context of how we teach math and what we as adults have acclimated to as aspects of the languages of math. Hamen did a study years ago with Asian children and identified that they have a considerable advantage over children growing up in the West. The basic number words in Chinese, in Japanese, and in Korean are single syllable, less to hold on to, and combine in a parallel way to the symbolic rules of the decimal system. For example, the number 21 would be expressed as 210-1. In English, in French, in Spanish, and other Western languages, the naming system is much more complex. It's necessary to master special words each time a multiple of 10 is reached. 11, 12, 13, 30. And in some languages, there are special constructions. Pardon me to anyone who is fluent in French for the miserable accent that I offer you. 453, literally 423, which in English would be 423, all right? So you have to be alert to the specific nature of the language of math. One of the ways we learn multiplication tables is learned by using our ability to remember patterns of sound, if we can, and if we have intact language systems. It's a great effort to learn the tables, the multiplication tables, that is influenced by what are called interference effects, that people who learn a second language, or in some instances, a third language, always do their calculations in their first language. So I had a colleague for many years at the Albert Einstein College of Medicine who spoke 5 languages. But her first language was Polish. And though she was most fluent professionally in English, whenever she calculated scores, she calculated in Polish. All right. So keep in mind as well that language struggles are embedded in math, as in so many ways math is indeed its own language. Listen to this next part. Listen. Replete with multiple meaning words. So when I work with math teachers, I focus them as best I am able early on to be aware of this, the language of math. Researchers at the John Moore University in Liverpool, England, studied a large number of preschool children and found this, that practice with letter sound interactions predicted the children's ability to count, calculate, and recognize numbers when controlling for socioeconomic class. Keep in mind that reciting the alphabet did not have a similar influence on teaching them to read. That relationship can be explained by language ability. Some aspects of number skills, like your ability to read and recognize numbers, rely to a certain extent on your vocabulary, all right? So one thought is that learning letter-sound correspondence gives children the tools to understand more abstract symbolic systems. Simply stated, the idea that a printed symbol on a page, the number 5, can stand for something else. So if children can understand this concept in relation to reading, S is represented by S, it might be easier for them to apply it to numbers than in math. Moreover, math, remember I was focusing before on multiple meaning words. Not only are there multiple meaning words, but there are homonyms. So for us as adults, some of the multiple meaning words are very obvious. Balance, round, scale. But others are even more confusing for the frequent nature of their use every day. For example, different, after, does not belong. Math is replete with multiple meaning words. We used to keep images, a list of the multiple meaning words in math to help the children recognize, think of the math meaning in this class. All right. Now then add to that the language challenge of the handful of homonyms. Homonyms, you may recall, is the words that sound the same but are spelled differently and have different meanings. For example, one, and I won that bet. Two, and I'll have some of that too. Four, oh, is that for me? I wear a size 8 shoe. Oh, last night I ate dinner very late. So children who have difficulty in vocabulary, in mental flexibility, in word knowledge, and in their general knowledge of how words are related to each other are liable to be confused more readily by the language of math unless teachers are alert and aware of the need to teach it. In addition to which, there is the sentence structure of math. If grammar is inherently weak in a student, then dealing with the grammar of math represents another challenge. Think about it. Plus and equals are mathematical forms of punctuation, all right? And then add that math has an infinite number of nouns. Just think of all the things you can add, subtract. But there are very few verbs in math. Plus, minus, times, divided, equals, to equal. So just think of the translation that is involved for a youngster. Sue has 2 pencils. Get ready for the multiple meaning word. She spends 1 hour at the store and buys 3 more pencils. How many pencils does Sue have in all? Lots of those words have multiple meanings, especially when you're in a store and you spend time, but not necessarily money. Right? The research is filled with the concept of academic discourse or the language of school. And math discourse is the specific form of academic discourse that's distinguished by word use, math vocabulary, what are called verbal mediators, graphs, symbols, diagrams, and routines, raising your hand to answer a question or raising your hand to ask a question. So, and there's also the notion of narrative in math, which is, it's sort of a specialized linguistic structure for math concepts. We talk in math in a specific way. We know, in summary, that there are 4 broad linguistic abilities that may impact a student's ability to construct, to store, and importantly, retrieve the way to solve a math problem, to construct, to create the problem, to store that information, and then find it when you want it. And those factors are reading comprehension, knowledge of math vocabulary, syntactic forms that have slightly different meaning in math, and the knowledge of symbols. Children in math have to shift back and forth between math language and general language, and they have to use the formal language of math to solve math problems, all right? Keep in mind that initially, calculation is an extremely effortful process that requires a great deal of concentration. Put a little asterisk next to ADHD and anxiety. It requires concentration, strategy choice, and enormous working memory resources. Next on that overriding slide from before are what are some of the diagnostic questions that we have to ask ourselves as teachers. And so when you work with a student who has a math learning disability, it's important to remember the potential subsets of math disability: the semantic, the language of math, the procedural, what are the steps and why do we use them, and the visual spatial. So is the challenge due to procedural, conceptual, or can he not find the words, the fact, when she needs them? There are also issues with math fluency, number sense, being efficient and being flexible. And it's always important to consider that there might be more than one difficulty lurking for this youngster. It's crucial to remember the youngster's strengths and areas in which she does understand and can use those math skills or math language, so that you can access positive experiences as a vehicle for dealing with where there are times when there are struggles. So we want to use their strengths wherever we can. These are questions, as you can see by Hamen, that you want to keep in mind, because there could be more than one difficulty in math. But which one is primary? And what are those cognitive or attentional or emotional or linguistic factors that are influencing? All right. There is more and more and more research for you to consider. So let me introduce you to Mathland. I have told this story many, many times. It was, Mathland was created by a colleague of mine very many years ago in a special education environment. We were in middle school, and the kids came into class, and a number was written on the board, and the teacher requested that somebody read it. It was 114 7/10, or 114.7. And the youngster raised his hand and said, oh, 114.7. And all of the other kids laughed at him. And that was when the teacher introduced the concept of Mathland. In Germany, we speak German. In France, we speak French. In Spain, we speak Spanish. And in this room, Mathland, we speak math. And that dot in this room is called either and 7/10 or point. And it was then that I began to work with children and teachers to introduce them to the concept that there is a Mathland. So what we tell the kids to do is, you're in Mathland now, turn your math brain on, all right? Turn your blank, this is, when you look at this, there is supposed to be, I beg your pardon, turn your blank brain off, turn your math brain on. Turn your science brain off, turn your math brain on. Make the shift from metamorphic, sedimentary, and igneous to the language of math, equals, divided by. We ask the teachers to teach multiple meaning words to the children, as we've referenced before, so they have access to that information as well. And heaven bless Beck and McCowan, the authors of enormous number of books on vocabulary instruction under the title Bringing Words to Life. Most of the language that they refer to as tier 3 words are specific to a content area. That is not always so true in math. They are often multiple meaning words that have frequent use. So we have to use vocabulary charts in math class to help the children know what those words mean in math class and how they ought to be used. And it is crucial that we require specificity in math language. Yeah, it's that one over there after the equals thing. What we want to do in that instance is to say, you just told me that it is the number that is following the equal sign. Yeah, that's what I said. I would make sure that that youngster then said exactly what I said, or repeat what I just said. It is the number that is following the equal sign, so that they learn to use the language of math and to be specific in doing so. I want to talk with you about a little bit about the importance of multisensory instruction. There's a very important distinction here to which I would like you to be alert. It is inherent in our program at Gateway School, and it is particularly important in our mathematics instructional program and math training for our teachers. The purpose of an evidence-based practice. We hear these terms, evidence-based practice and research-based practices, and people tend to use them interchangeably. Let me clarify a little bit for you. The purpose of an evidence-based practice is to use the best evidence available to make patient or student care decisions. Whereas research is about developing new knowledge, research-based practices, all right? So what we know is that evidence-based practice involves innovation in terms of finding and translating the best evidence available into effective practice. So for literacy, we have Orton-Gillingham-based instruction. It is well regarded, the literacy wars, oh, they are small battles here or there, but by and large, it is understood that multisensory instruction and not, that includes the preparatory work in phonics, is essential. What we know is that there isn't an OG, an Orton-Gillingham per se, for math. Orton-Gillingham instruction focuses on the multisensory, on structure, on step-by-step analysis, data-driven, and highly individualized. There's no OG program for math. However, the best math programs are multisensory, data-driven, make a direct connection between previously learned and new material, and crucially, provide immediate feedback so that a mistake doesn't ever get the chance to take root. An error is made on the page in a simple calculation, teacher points right away. Take another look at this. Let's fix this calculation. Let's fix this addition problem. So 3 plus 5 doesn't get to take root as 7 because the child has calculated wrong. Here at Gateway School, we are committed to using a multisensory approach that does all of the above and follows the following sequence: concrete, representational, abstract; concrete, hands-on; representational, pictures; abstract, converting the information to numbers and symbols. And there was a reason I thanked some of my colleagues when we started, because these are not easy curricula to develop. They require a high degree of effort, nuance, and detail. How else do we teach in general at Gateway School, but always in math? This is particularly crucial. The notion of being meta. We model the process in which we are involved. We know that children with learning disabilities often do not speak so well, or as I couldn't resist, talk so good. This is a reference to all of those boys and girls with specialized and particular needs who are now included in mainstream classrooms. Inclusion is the model of education in our country now. And I don't have to tell many of you that it can be hard for some of these kids to explain what they understand or think they understand or do not understand. So when the children are included and the teachers are not trained to recognize the patterns of errors, it makes learning in general harder. For us at Gateway, we are fully aware of their needs in that regard. Model your thinking. This is the work of Hamen. When a teacher models his or her thinking, students begin to realize, especially in math, there's nothing magical about getting to the solution. I'm looking at this equation, and what I see is, wait a minute, I think I'm supposed to solve for, oh, I remember the first step is always because there's a process. And though they will roll their eyes at us, it is important that they say these words in much the same that we do, initially out loud and then to themselves. The modeling helps the students. And really, we all know, especially these days, that we're talking to ourselves more and more out loud. But talking to yourself helps. It helps to guide your thinking, alrighty? So it helps them work through every step. It helps them see how to correct mistakes. It encourages them to be aware of their own thought process so they know when they've made a mistake. And the questions that you ask them are designed to help them see a pattern, get a sequence in their thinking, and figuring out their wrong answers. So what did you do here is not a question that will help guide. But let me see, what step did you do before this one that led to this answer? Let's go back through it together so I see how you were thinking, alrighty? And what do you do when a kid says, oh no, which we know is the get out of jail free card. Oh no, oh remember. The trick in that one is, okay, let's do this together. And then you can ask different levels of question. Well, did you write a 7 here? Ah, am I letting you know that that's the right answer? That that's not the right answer? Ah, so you do know. And you identify what they do know to get them in the process with you. Alrighty. Be meta, model thinking, and teach them to think the same way, out loud. We work very, very hard to create micro units. I'm going to do it. I'm going to model this skill. Then we're going to do it together, and I'm going to give you more feedback than you could ever imagine getting. All right, and then you do it as well. You see that word explicitly? We teach explicitly, step by step, piece by piece, in little staircase, and in little steps up a staircase to completion. And what we do is help the children see all of the parts clearly and how they are related to the whole. And I'm going to say something very deliberately. I beg of you. And if my mother were watching this, her wisecrack now would be, oh, Lydia, don't beg, you're old enough to steal, which she always says. I beg of you to remember that just because you taught it does not mean that they learned it. It doesn't. Talking isn't teaching. Teaching is understanding the needs of the learners, using your knowledge of the content in conjunction with a huge repertoire of techniques that we hope you have, skilled use of language, and awareness and accommodation for other aspects of learning, like working memory, like executive functions, like emotion. So you see what we do with this image here: model the skill, teach it explicitly, have them practice, and steadily as they improve, increase and raise the expectation for them until they're at the top of the staircase and can do it themselves, all right? What we have to do is to adapt according to the circumstances of this particular learner, with the knowledge that learning is a process. It is not a simple event. The next recommendation, based on what we do at Gateway, is to encourage verbalization. I've deliberately offered you examples of how kids make mistakes, and what you must be alert to doing as an educator is taking that mistake, rephrasing it, and allowing the child to hear the correct version and use that language. Oral rehearsal makes the students' difficulties clearer to the teacher. So for example, if a youngster says, 2 and X, yeah, 2 and X, when he means 2 times X, that's diagnostic. And it's also remediable once you've identified it, all right? So by verbalizing and using accurate language, both in teaching and in learning, students can be helped to be much more aware and much more vigilant about simple differences: 2 times X versus X squared. They are not the same. And again, it's a symbol that you do not see in the world. It's not like the Mercedes image, or the Volvo image, or the Toyota image that we recognize to stand for a word. X has a meaning that is very specific. So we want the kids to tell us what they're thinking. It allows us to hear their thought process. It allows us to give them the language that they need. And as you can see, it facilitates, enhances, permits teachers to give very specific feedback, and it gives us very important diagnostic information about the child's misperception or misconception. Encourage verbalization. That gives you information. All righty. So this is a discussion now that is important in terms of introducing a new skill. This works. This is the work of Perlman, and it involves 4 different component parts: the task analysis, the breakdown, the learning process, and constant review. I'm talking to you about good teaching, and this is applicable in math as we do it at Gateway School. Here's the question that you have to ask yourself. Do my students know all the underlying skills necessary to do this new task? Remember, we talked about math being cumulative, much more than many other subjects. Am I going to be able, or how shall I be able, to help my students make the necessary associations between what their old skills are and their new skills are? When they're counting by 5s, when they're counting by 10s, we taught them to use rhythm. Do they know that can be applicable for any table? Have I broken this down? Micro units. Have I organized my lesson with small segments, starting with the simplest and moving to the more complex? You build up, all right? And does my lesson proceed from the mechanical to the meaningful, from the concrete to the representational to the abstract, all right? Have I, as a teacher, set up this lesson to demonstrate that you can generalize this skill? It's not an isolated skill, that it can be used in other situations. Can you imagine by now how exhausting it is to be a good math teacher, to be a good teacher in general? Certainly at our school. Have I considered a system of attack? Are all the steps obvious to the children, either on the board, on a work page, or in a math folder? Is my lesson multisensory? Is it spatial, kinesthetic, and visual? And are we talking about using verbalization to talk about what we're seeing? And very, very importantly, we call this the exit ticket. Have I left time and the opportunity for the students to retell me something they learned using their own language before they leave my class? Because that way I get to hear what they have understood. We constantly have to review. Am I keeping track at all times of what I've taught them and how I can integrate it into future lessons? All right. And that's why we always have warm-ups for the kids at the start of a lesson. I will tell you very sincerely, make no assumptions. Teach everything. And the kid who's got it, terrific. Let him move ahead a little bit. Learning is a process. I want to talk a little bit, especially in math, about the issues of memorization. I do not know how I learned the times tables. I know that I recited them till I might well have been blue in the face. Nobody taught me the relationships. In the New York City public schools a few years ago when I was in school, we were made to memorize every night. Practice, practice, practice. So what we know is that students' understanding improves when they are taught to create meaning. All right? When they are taught to create meaning instead of simply learning mathematic algorithms, and shortcuts to solve problems. Alrighty. It's necessary to build these in order to establish fluency, but waiting to introduce them until after the students begin to comprehend the idea can be beneficial. This is the work of Hebert. It's important. It's an important citation. There is evidence to show that it is harder to teach understanding of a concept after the procedure to solve it has been memorized. All right. And when a youngster says, just tell me what to do, I don't care if I understand it, that's not the best way to teach a child. Now, that said, neuroscience has shown us that learning involves the creation or strengthening of neural pathways in the brain, and that is achieved by repetition. All right. Repetition, we know, can and does facilitate learning and recall. So some have argued that basic math education must include rote learning. Alternatively, there's research that shows that rote learning alone produces a narrow and brittle form of knowledge in which you can recite and reproduce what has been learned, but not necessarily understand new information related to it or to make practical use of what you've learned. Here's the bottom line. Bottom line, to produce usable, applicable knowledge and to generate useful mathematical skills, rote learning must, underlined, must be accompanied by understanding, not a replacement for it. Math is an activity. You do it. It's like driving a car or like skiing. It depends on basic mastery of skills. And the necessary, it's necessary, all right, the necessarily understanding needs to be coupled with rote learning. Neither can succeed, one without the other. And so I'm going to give you again a literacy analogy. Decoding plus comprehension equals reading. Decoding the words off the page without understanding what they mean is not reading. Reciting the times tables without knowing how to use them in calculations is not effective mathematical application. So let's talk a little bit about the nature of learning disabilities and what does work and what doesn't work for our children who have learning disabilities. There's basic terminology, as some of you may be already have familiarity with. Math disability is referred to as dyscalculia. It refers to those children with markedly poor skills at deploying basic computational skills and the cognitive processes, the thinking to solve problems. Kids with dyscalculia may also have deficits in language, in retrieval, in executive functions, in working memory, in visual spatial skills. Remember the image of who is this child. There's no fully, we all agree, there is no two ways about it, consensus definition of a true math disability. It shows up in different ways in different literature. Now, it's important to know that math disabilities are not particularly rare, although they have, and until fairly recently, received far less attention than issues related to literacy. A lot of attention now is being paid to issues in mathematics learning and difficulties in doing so. Math disabilities can be very intertwined with other learning disabilities. And there has been some research that I've uncovered that's demonstrated that 40 to 50% children of the children who are classified with reading difficulties and other learning disabilities also demonstrate math disabilities. This can have a significant impact on a student's functioning in school, a student's sense of him or herself, and as we discussed earlier with employment. Keep in mind that dyscalculia is considered a neurodevelopmental disorder. we know much more than we ever did. And as I noted before, dyscalculia implicates or involves a large number of other underlying cognitive processes, including language, memory, visual functioning. It's not simple, this business of dyscalculia, and it's not yet fully understood. These complex processes underlying math disabilities are represent the ways that in which neuroscience accounts for varying degrees of math disabilities. People use the word dyslexia for many, many, many different meanings, and so too is the word dyscalculia being used that way now. I think it's important to note, remember my son, now a grown man, who was in the second grade with the teacher who didn't like math and so she didn't teach it. Not all math disabilities are inborn, all right? Some are created. Some are created in school as the result of poor or inconsistent instruction, inadequate resources, or inadequate teacher training, all right? So here's a little quickie on dyscalculia, plain and simple. In a talk that involved a lot of very complex language, I've been trying, here it is, plain and simple. Dyscalculia makes learning math hard. It's more common than you realize, all right? There are a lot of people who have trouble working with numbers and understanding concepts like bigger and smaller. And again, little kids who have restrictions in language think of bigger and smaller as related to size and height. Being able to be mentally flexible, all right? It's much more common than we realize. And you know what? You may know someone with dyscalculia who is an enormously intelligent, successful person, all righty? That's why in part why I undertook and accepted this responsibility, because it was an opportunity for me to learn about an area of my functioning that has never been my great strength. By and large, it's often overlooked. And that's what they used to say, oh, she's just not that good at math, all righty? Dyscalculia, signs of it can show up as early as preschool. That's why I started there, but they often go unnoticed. And nobody pays attention to it when they're little, because the expectation is that you don't really need to do math until you get older. No, 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 no. You do not build the second, third, fourth, fifth floor and the penthouse, otherwise known as AP calculus, without having laid the foundations in the very, very early stages. This is, as you can see, the work of Geary and Mersanen in regard to a math disability profile. So let me give you a little bit of information about these specific areas here. The typical math disability profile, and this is, again, this is important as it is part of diagnostic teaching. These kids are slower in basic numeric processing tasks, which in English means they can't very quickly identify numbers. They are not facile at making comparisons between different numbers of different magnitudes, and they cannot readily count forwards and backwards, all right? They struggle in determining quantitative meaning of numbers. That means they don't use strategies very well, and they do not always visualize very well. That involves your need to, you recognize that you can structure your lessons to accommodate that difficulty. Some kids have difficulty learning basic calculation procedures necessary to problem solve, and you recognize this kind of error. They're prone to procedural errors, such as saying 7, 8, 9, when calculating, trying to solve 6 plus 3. So they have 6, 7, 8, 9, and then they have the wrong fingers in the air. By the way, use your fingers, that's part of why they're there. Or they misalign numbers, 25 plus 3, but the 3 is put under the 2. And sometimes they use incorrect computational processes. For example, the school store sold twice as many pencils to Sam than to Robert. If Sam was sold 4 pencils, how many pencils were sold to Robert? The answer is 8, not 2, because of the word twice, which typically means 2 times. The kids lock in to a particular aspect of the language and misuse it for computational purposes, and or they cannot retrieve computational facts. 7 times 6 is not 35, alrighty? However, starting to sound dour, hope springs eternal. With continued research, with informed teacher ed programs, improved diagnostic processes, and skilled and knowledgeable diagnostic teaching of the kind that we are very proud to offer at Gateway, these are the children that we will see learning and learning math. So let me tell you a little bit about our Gateway program for success in mathematics learning. You can see, you've heard me refer to some of these points before. At Gateway, very specific attention has been paid to math learning and mastery, the components of math, the array and the nature of difficulties, the amount of effort to adapt the programming, and to the nature of the adaptations that have to be made. Extensive teacher training in concepts, instruction, and systems and techniques for teaching, and the stress on diagnostic teaching and being able to be flexible and adapt and create adaptations to learner needs. We have math-specific coaches and curriculum developers. So there is our model of instruction, direct and explicit, which concentrates on observable behaviors for the kids, breaking down the tasks, very clearly defined and consistent methodology. And we model, we give explicit directions, immediate feedback, and reinforcement. This is the math program of which we are so proud. All right, what we have done in the Gateway to Mathland for our learners is a modification of standardized programs. What has been done is an adaptation of Singapore math, and you have heard me reference the concrete, pictorial, and abstract before. We modified this program. I shouldn't say we. This program was modified by exceptional people because it had to be done in view of our understanding of who these children are and how they learn, and therefore how, the ways in which they must be taught. The program is structured in hierarchical phases, as I mentioned earlier, the concrete, the pictorial or representative, and the abstract. Singapore math was developed for typical learners. So for example, it has multiple textbook lines, and if you are unfamiliar with Singapore math, each textbook has a sequence of skills to be taught, which is not unfamiliar to most math programs. It is notable that those might be taught in a single lesson, all right? Singapore math for children who struggle with math learning must be broken down and taught in multiple lessons with consistent review and reestablishment of these essential concepts. These adaptations for our Gateway boys and girls are made at multiple levels in order to meet the specific needs of the learners. So modifications are of the order of individual skills within a concept based on what we know about a child. Most strikingly, for the children with visual spatial challenges, handwriting and organizational challenges, working memory issues, sequencing challenges, there have been worksheets that are created with the procedural steps, the task breakdown, and space provided along with a sequence of cues for the steps, all right? The message here is to think of the skills that need to be taught in a global, overarching manner, as well as for specific lessons. Now I'm gonna interrupt because I want you to see this slide again. Here is what our belief system is at Gateway School. I want you to keep this image in mind when you are thinking about how you are going to be the most effective math teacher, or for our Gateway families, how your children are being taught. The components of who is this child are always, always considered. They are looked at individually by need within the context of a larger group. And the effective teaching model says, what do I have to teach this child? How do I have to teach him? And why must I teach him that way? Not only the content, but the underlying skills. And one of the proudest moments I have had in the development of classroom language dynamics and this model of who is the child and effective teaching model was listening at graduation from Gateway last year. One of the students, as he stood up and made his speech, talked about how his teachers had helped him understand the way he needs to learn, how he learns and why he learns that way, and what he can do as an advocate for himself. So as we come to a conclusion, there are the 4 components of Gateway's math instructional program. You can see them here. We will stress, again, the concepts that are to be taught, the language that must be used, the development of number sense, understanding what numbers mean as they evolve to the ability to compute, and then the application using those numbers to solve word problems, which is a language-based skill as integrated with mathematics as it can be. And we rely always on direct instruction. And see that next one? Task analysis, task analysis, task analysis, and more task analysis, to break every task down into little pieces, to understand all of those little micro units and steps that a child may need to be taught in order to achieve the competence in that particular task. We teach them to talk to themselves in their heads and to understand that repetition is not boring. It is a way to practice. And any great athlete spends hours and hours and hours hitting tennis balls, hitting baseballs, and any really devoted student will work on constant repetition until he becomes fluent and automatic. Trust me, Roger Federer does not think about his backhand, all right? So, but we constantly do, and it's part of the Singapore math, is practice with a spiral, refresh and renew and invigorate. Practice what we've learned and move forward. I want you to keep in mind that what we do here is slice and dice. We analyze every skill that's to be taught, every skill. And we think about who needs scaffolding for organization, who needs scaffolding for working memory, who needs scaffolding for graphomotor skills. We are looking at a direct instructional model, and it allows us to be able to know what we did so that when something doesn't work, we can analyze what went wrong. Further, and this is important, when we are looking at a task analysis, this is a very important analogy. We integrate other familiar systems and strategies for our students. For example, at Gateway, we use an approach called story grammar marker for reading and math. And so as such in Singapore math, where, which calls what are typically known as word problems, story problems, we use the story grammar marker system as a scaffold because the children are accustomed to that in ELA. So as such, we have an application of computation via a task analysis using a familiar system from another classroom, all right? Practice, 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 and more practice, all right? Our students, we know, don't retain easily. So we don't move quickly and we don't jump from one thing to another. And as a result, our Gateway students feel this way about learning math at the Gateway School. Thank you all. I know you have been sitting with me a long, long time. I hope you have learned something that you can use and that you have optimism about math learning and a deeper understanding. Thank you all so very much for lingering.
Okay. I think. Well, thank you everyone for joining us. We have a couple of questions. I'm not sure if people can see me, but
Yes, you're visible.
well, I can see you. Not sure if everybody else can, but so
And I won't do anything untoward.
okay, good. So great. So a couple of questions came in. Some of them you ultimately answered, but I think they're worth kind of looking at. Someone asked, how do you teach explicitly to students who struggle and still provide opportunities for them to construct their own meaning and understanding without just copying what you did?
Oh boy, oh boy, oh boy. How
Big
much
question.
time do we have? How much time do we have? I'm going to tell you a story that will help answer that question. When I was consulting in another school in New York City, it was a class with a general education teacher and a special ed teacher as co-teachers. And they were confounded. They really were flummoxed by this one fellow who could do remarkable mathematical problems in his head, but he couldn't do very much on paper. And he couldn't explain how he did it either. So I asked him to teach me what he was doing. And he was attempting to take me step by step through this complex maneuvering that he did. And very quickly I was able to see that this wasn't going to work with higher numbers. And when we hit that anticipated roadblock, I said to him, what do we do now? And he kind of looked. That had never happened to him before. So we went back and I started to teach him the more traditional system, but having been introduced to his methodology, took some of his strategies or styles and integrated those that would always work for him. So how do we teach them? As I said, it's direct, explicit instruction. And sometimes the kids will say, no, not that way. I don't get it that way. You got to do it this way. What you do is strike a deal. This is the way we do it at our school. I'm going to teach you this way. And then you're going to teach me your way. And we're going to agree on when and how you can use some of your strategies if you can prove to me, as your teacher, that they're going to always work. In my experience, all too many times, they don't always work.
Okay. Someone asked, and I think you ended up talking about it, but if you want to go back to the who is this child slide. So you had mentioned it earlier in the presentation. So some people had some, questions about who is this, the image was.
This one, is that what they're referring?
Mm-hmm.
Oh, I'm sorry, Ms. Ironside, what was the question?
Just who is this child as it shows up in your presentation?
Okay. Who is this child is a conceptualization that, as you saw at the end of the talk, is part of the program that I've developed called Classroom Language Dynamics, which includes the who is this child and the effective teaching model. It is a way that I train teachers and at times parents to think about the child standing before them and to understand that there is a dynamic between and among all the potential aspects of the child's neurology, his or her temperamental style, his or her personality style, and all of these other components that are often discussed independently, but in fact are interdependent. Example, I'm a mother of twins. They could not be more different in temperament and personality than I can't even imagine what than black and white. They're two entirely different fellows. I have been in situations where people will say to me, oh no, it's just that he's got an attention deficit. To which I say, when he has an attention deficit, it also impacts all of the other components of his functioning potentially. So if you have sensory motor issues, I'm not scratching myself for no good reason. There's a tag that's driving me crazy back here. That's going to affect my attention. So I train teachers and parents and physicians to say, who is this child in regard to all of these components, because kids cannot be boxed as easily as curriculum or curricula sometimes try to affect. And we work very hard at Gateway School and in some other schools as well to be answering, who is this child and how must I teach him, because of the answer to the questions in each of these domains. I hope that's helpful to you.
I think so. So a couple of questions are specific to Gateway, which I'm happy to answer. Someone asked how many students are in a math class at Gateway. Gateway has a skills-based groupings system. So the students are grouped together mostly by their skills in their specific area. So for some students in math, they're very good at calculations, but not as strong in word problems because of language-based, because of some reading difficulties or some language difficulties or language processings. Or other students are, again, sort of have that more conceptual knowledge, but their executive functions are more disrupted, and so we group them together by that. So we can have a group as small as 2 or 3 students, and as large as between 8 and 9. We don't typically go over 10 when it comes to the groupings for math and also for reading, because immediate feedback is such a large feature of our school that over 10 the teachers need it. If there's going to be more than 10, there's usually an assistant teacher in the room so that they can have the immediate feedback. Another question about Gateway was about the kinds of scaffolding that we use at Gateway for issues like executive function and retrieval and recall. Dr. Soifer mentioned some of them. Some of the scaffolding that we do and some of the skills that we're teaching are really about not so much that we're giving them the scaffolding, but that we're teaching them the strategies that they need in order to kind of compensate for some of those difficulties. So that's when Dr. Soifer was talking before about the difference between a strategic learner and a not strategic learner. We're really thinking about the kinds of scaffolding that we can do that is really a strategy that the students then can use themselves. But typically, if you're thinking about word problems, we have a pretty, we are really doing a task analysis and breaking down each skill that's embedded in completing a word problem and teaching that direct skill and then building it back up. So the students aren't doing word problems completely independently right away. They're learning each particular skill, and then as they learn and master one skill, we add in the next one. And we have an 8-step word problem boot camp, as we like to call it, for those kinds of difficulties. So the students are learning how to check off each step as they go, as a way to kind of keep track of and not have to hold on to all the steps themselves.
And Heather, it's also true that when they're doing that, we are doing the piece that I referred to before as the meta. Tell me how that helps you. Remember how that helps you to check off the steps. So it's not just doing it, but it's being cognizant of the benefit of doing it and verbalizing it, saying it out loud.
Yes. Someone asked about for students with autism, how would you teach word problems for those students?
Well, it depends, because when a person has autism, there are components. So of who is this child? What is the intellectual ability? What are the executive functions? How flexible is that student's language? The nature of the personality. I've known people on the autism spectrum who are very interested in other people, albeit within a constrained area. So I would say that depending upon the dominance of the autistic features that the child is experiencing, you would have to teach him or her in different ways. There is a tendency among people who are on the autism spectrum to have a certain rigidity in thinking style. So that would involve, as one example, these are the circumstances in which we use this procedure, but we don't use it for this kind of problem solving. So that it's clear and detailed and constrained, so that the youngster can say, oh, I understand. When I add, I always have to put a plus and an equals. And if somebody has more, I might have to subtract, so that you are giving them the cues. It involves a fair amount of detail and control of that detail for a person who might not be particularly flexible in thinking style.
Okay. So another question was about whether or not teachers will look at using a procedure to solve a particular problem. So if we are teaching multi-digit multiplication, will we look at a different procedure to do this? We are following the Singapore math curriculum. So typically we are teaching them using those procedures. If it's not working for a particular student, we do like to be diagnostic about in our teaching and thinking about the cognitive linguistic orientation. So we're sort of thinking, what are the other areas that might be impacting why this particular procedure isn't working, and try to accommodate it that way. And a little bit, somebody wanted to know a little bit more about the Stern math program that we have used with our youngest learners, and why and how what the positives and benefits and effectiveness is it before we switch over to the Singapore math program. And Lydia,
I'm not sure that I'm best suited to address that.
Right. So I think that in for Stern, one of the reasons I think that we typically use it as to begin with our youngest learners is that it's very multisensory. And it really lays a strong foundation for the Singapore level 1. And it's also because it's language, kind of really looking at building that foundational math language that you were thinking about. So the more, less, bigger and smaller and taller and shorter, those are all concepts that are taught in the Stern program. So that's one of the reasons that we use it for our youngest learners, and then before moving them into the Singapore program. And 2 more questions. One was about our reading program. We use PAF for our students, and then we use some other, we've sort of developed a collection of other Gillingham-based reading programs for our more adolescent who are moved out of PAF but are still working hard on decoding and fluency. And the last one, and I think which is will probably come, is there a good book about math language for different groups and branches in math?
There are numerous books on math. Rather than getting up and going to my library, what I'm going to suggest is whoever had that question can send it to me at my Gateway email, and I will then provide some sources for parents on the language of math.
Sure. I'm going to type in your email address so that they can.
Thank you.
You're welcome. And I think we have so far answered everyone's questions. And other people are sharing in the chat as well. So I am going to let us all go. Thank you very much for joining us this evening. We very much appreciate it. It, you know, was nice to learn about something that wasn't related to distance learning, but can certainly be applied to. And we look forward to hosting these in the future. Thank you, Dr. Soifer, for having us.
Very welcome. Good night, everyone. Thank you for joining.